This is lecture 5 of differential equations models in epidemiology. The topic of this lecture is spontaneous human behavioral change in epidemiological models. The models that we've discussed so far are missing something, and we might as well put it out there on the table. In the models that we've considered so far, human behavior is not affected by the course of the epidemic. The parameter beta, the effective contact rate, which measures how much people are interacting, does not change as the epidemic proceeds. In the models we've discussed so far, it's a constant. You know from experience that this is wrong. As the number of infectives rise, many susceptibles are going to react by staying home, practicing improved hygiene and social distancing, wearing masks. They will be afraid of getting the disease, and their behavior will be affected. As a result, as people stay home and reduce their contacts with other people, beta falls. Later, if the number of infectives falls as a result of fewer contacts, susceptibles might start to relax, and as a result, beta rises. This is clearly important for the actual course of an epidemic. How can we model this? We're going to present a way of modeling changes in human behavior during an epidemic that is suggested by game theory. What is game theory? In a calculus class, you learn about optimization problems. You learn, for example, how do I arrange a rectangular fence so that it will enclose the largest possible area? Game theory is about another type of optimization problem. You're trying to maximize your own payoff, but this time your payoff depends not only on your own choices, but on the choices of other people too, which you don't have any control over. The side of game theory that uses differential equations to model how people's choices change in response to the changing choices of others is called evolutionary game theory. We're going to use an idea from evolutionary game theory called imitation dynamics. In imitation dynamics, people randomly encounter other people who might be using a different strategy to deal with a situation than the strategy they are using. And if the strategy of the people that they encounter is producing a better payoff than their own, they will tend to adopt the strategy of the other people. We're going to consider an SIR model in which susceptibles can choose between two types of behavior. Normal behavior with an effective contact rate, beta n, and careful behavior with an effective contact rate, beta c. Careful behavior is the type that results in fewer contacts with people, so beta c will be less than beta n. What are the payoffs of normal behavior and careful behavior? We're going to assume a baseline payoff of normal behavior independent of the epidemic of 0. This is often done in game theory. You just pick a baseline payoff, call it 0. In the presence of an epidemic, normal behavior will have an additional payoff of a negative number times the number of infectives. This is because you might get the disease from the infectives that are out there. And the likelihood that you get the disease is going to be proportional to the number of infectives that are out there. So the payoff of normal behavior is a negative number, which we call m sub n, n for normal, times the number of infectives at present in the population. What about the payoff of careful behavior? Well, you still might get the disease. You still might encounter those infectives out there, no matter how careful you are. So you're still going to have a payoff of minus MC times I. MC will be smaller than MN because your likelihood of getting the disease will be less. You're encountering other people less. But in addition, you will have a negative payoff of minus K. K is a positive number, just from the fact that you're adopting careful behavior. You're staying home, so you're not seeing your friends. You're not seeing your family. If you have to go find work every day to pay for food, if you stay home, you're not going to find work. You're going to run low on cash. You won't be seeing your friends. Careful behavior has an intrinsic negative payoff. That's why people weren't doing it before the epidemic struck. So which behavior gives a higher payoff, normal behavior or careful behavior? And the answer is, it depends. So let's look at normal behavior minus careful behavior and see whether that comes out to be positive or negative. For normal behavior, we put in a minus MNI. There it is, minus MNI. And now when we subtract the payoff of careful behavior, subtracting a minus K gives us a plus K. And subtracting a minus MCI gives us a plus MCI. The two minuses here make a plus. And I've grouped the two terms involving I so that the difference in payoffs between normal and careful behavior is K minus MN minus MC times I. Now remember, MN is bigger than MC, so MN minus MC is a positive number. So the difference in payoffs of normal and careful behavior is K minus MI. K is a positive number, and because MN is greater than MC, M is a positive number. Okay, so which behavior is better, normal or careful? Normal behavior is better if this difference is positive. Careful behavior is better if this distance is negative. The answer is, it depends on I. If I is smaller than K over M, this difference will come out positive and normal behavior will give a higher payoff. If I is bigger than K over M, this difference will come out negative and careful behavior will give a higher payoff. That's perfectly understandable. When the number of infectives out there is small, normal behavior is not that bad. You have a low probability of catching the disease anyway. When the number of infectives running around is high, careful behavior will give you a higher payoff. Despite this payoff of minus K, the lower probability of catching the disease will result in a higher payoff. Now let's describe imitation dynamics, this idea from evolutionary game theory. We're going to let X denote the fraction of susceptibles that use normal behavior, and 1 minus X will denote the fraction of susceptibles who use careful behavior. Of course, the two fractions add up to 1. Susceptibles using normal and careful behavior encounter each other at a rate proportional to X times 1 minus X. This is exactly like susceptibles and infectives encountering each other at a rate proportional to the product SI. Exactly the same idea. If an individual encounters someone using a behavior that gives a better payoff than her own, there's a reasonable chance that she will change toward using the other behavior, since she's just learned that it's superior to her own. So what is the rate of change? How quickly do people change their behavior? X dot, the rate of change of behavior, should be proportional to the rate at which these people using these two different behaviors encounter each other. And we're going to assume it's also proportional to the difference between the payoffs. In other words, if the difference between the payoffs is small, you would expect people to change their behavior slowly. If the difference between the payoffs is very large, you would expect that to encourage people to change their behavior quickly. The difference between the payoffs we showed on the previous page was K minus MI. So here's the rate of change of X. Rho X, 1 minus X, K minus MI. Now what we should notice is if I is small, if I is less than K over M, then this number here is positive, everything is positive, and that will result in X dot being positive. In other words, when the number of infectives out there are low, normal behavior is better, the fraction of people using normal behavior will tend to increase. On the other hand, when I is greater than K over M, this difference here will be negative, X dot will be negative. That means the population fraction using normal behavior is decreasing. With a high number of infectives out there, people will tend to use careful behavior. The percentage using normal behavior will be decreasing. Let's put this all together and get a full system that models at the same time the progress of the epidemic and the changing behavior of people in response to the progress of the epidemic. This is modeled on the SIR model for simplicity, and we've ignored the recovered category. You may remember that in the SIR model, S dot was minus beta SI. This is the same thing, except now we're using an average value of beta. A fraction X of the population is using behavior that results in a beta of beta N. A fraction 1 minus X is using behavior that results in a beta of beta C. And so the average or mean value of beta is this term. I dot in the SIR model was beta SI minus gamma I. And here in place of beta, we of course use the average value of beta that we got from up here. What about X dot? X is our other changing variable. Well, we saw that X changes in response to interactions. That's this term. But there's one other term here that we haven't explained. X times 1 minus X times beta C minus beta N times I in the X dot equation. We're not going to go through the derivation of this term. It's in the book. But what I want to point out is that this term is always negative. Beta N was bigger than beta C. So here we have a negative term. X and 1 minus X are positive. I is positive. This term is negative. This term says that the percentage of susceptibles using normal behavior tends to decrease. Why is that? The susceptibles using normal behavior are more likely to catch the disease than the susceptibles using careful behavior. When they catch the disease, they move out of the susceptible compartment and into the infective compartment. And that process all by itself would tend to reduce the fraction of susceptibles using normal behavior, just because those people are more likely to catch the disease and move into category I. What is the phase space for this differential equation? The set of SIX triples that we actually care about. It's a prism. We'll draw a picture of that on another slide. It's a triangle crossed with a little interval. It's the set of points SIX such that S is at least 0, I is at least 0, S plus I is no more than 1. That's the triangle in SI space. And then X, the fraction of susceptibles using normal behavior, has to be between 0 and 1. It's an interval. We're going to make some assumptions about the parameters in this system of differential equations. First, beta N over gamma, that's R naught for people using normal behavior. We're going to assume that beta N over gamma is greater than 1. In other words, normal behavior would yield an R naught bigger than 1, which would tend to make the epidemic spread, at least at the beginning when there's lots and lots of susceptibles. We're going to assume that beta C over gamma is less than 1. In other words, the R naught for the susceptibles using careful behavior is less than 1. If all the susceptibles were to use this careful behavior, this assumption says that the epidemic would just die out. The careful behavior is that important. It could reduce the number of contacts so low that the epidemic would just die out. Our third assumption is that K over M is smaller than 1. That means that the level of infectives at which this term up here switches from positive to negative is between 0 and 1. That just says that both normal behavior and careful behavior are sometimes preferable. For some level of infectives, normal behavior is preferable. For some level of infectives, careful behavior is preferable. And our final assumption is that the number rho here is big. What that means is that behavior can change pretty fast compared to the time scale of the epidemic itself. And that kind of makes sense, especially in the modern world. Here we were talking about the rate at which people using different types of behavior encounter each other. What kind of encounters are there in the modern world? Well, you can run into somebody on the street and talk to them, but there's other types of encounters in the modern world. You can see their Facebook posts. You can exchange text messages and emails with them to see how they're doing. And because this kind of contact can have a high frequency, it's quite reasonable that people could change their behavior very quickly if they became convinced that their current behavior is not the appropriate one. So rho is large. What we'll see is that this system can produce an epidemic with waves. The number of infectives can rise, then fall, then rise, then fall. We can get several waves of an epidemic. That just doesn't happen with the simpler version of the SIR model or with the COVID model that we looked at the other day. There are actually two different time scales in this problem. This is quite common in problems of the applied sciences. So let's look a little more carefully at what's going on here. Here's the system of equations that we wrote down on the previous slide. We said that rho was large. To express that, we're going to write rho as 1 over epsilon, with epsilon a small number. Epsilon is often used in mathematics, as you know, to designate a small number. 1 over a small number is a big number. Nobody likes fractions. We don't want a 1 over epsilon here. So we're going to multiply the last equation through by epsilon to clear that fraction. And that will result in an epsilon term right here and an epsilon term in front of the x dot. Let's recall that dot means derivative with respect to t. And t, the time scale appropriate for the epidemic, it's always been days. T is going to be called slow time. So here's the system I just wrote with derivatives with respect to t, the slow time, and epsilon out front of one of the equations. Now we're going to look at the other time scale that exists in this problem. Let tau equal t over epsilon. Tau is called the fast time. So for example, if t was time in days and epsilon was the small number 1/24th, then tau would be 24 times t. Tau would be time in hours. Hours would be the fast time, appropriate to things happening on a faster time scale. So I want to rewrite this equation so that the derivatives are with respect to tau, the fast time, instead of with respect to t, the slow time. So how do you do that? Well, by the chain rule, the derivative with respect to t is the derivative with respect to tau times d tau dt. D tau dt is 1 over epsilon. So derivative with respect to t is 1 over epsilon times derivative with respect to tau. We've used a dot to mean derivative with respect to t. We'll use a prime to mean derivative with respect to tau. And now I just want to rewrite these equations so that all the derivatives are with respect to tau. So here where we see a ds dt is 1 over epsilon ds d tau. So I will replace ds dt by 1 over epsilon ds d tau. And since I don't like fractions, nobody likes fractions, we'll multiply through by epsilon, and we'll have ds d tau equals minus epsilon times what we had before. Similarly, up here, di dt is 1 over epsilon di d tau. So we just substitute for di dt 1 over epsilon di d tau and multiply through by epsilon. We get the same right-hand side, except epsilon is multiplying every term. And now, in the last equation, epsilon dx dt, what we have here, would turn out to be epsilon times 1 over epsilon dx d tau. In other words, it's just dx d tau. So in the last equation, I simply replace epsilon dx dt by dx d tau and don't do anything to the right-hand side. There's no fractions to clear. So here is the system written in the fast time scale, derivatives with respect to tau. This is called the fast system. The other is called the slow system. And this sort of system that can be written with respect to either slow time or fast time is called a slow-fast system. The way one studies these slow-fast systems these days is using what's called geometric singular perturbation theory. Another approach is very analytical. You write down power series and t and tau and match them. But the more common approach today, I'd say, would be this geometric approach, geometric singular perturbation theory. So what I want to point out is that for epsilon greater than 0, the fast and slow systems have exactly the same orbits. The fast system, if you look at the right-hand side, it's just the slow system multiplied by epsilon. The two systems, their right-hand sides would be almost the same, except that this system down here is obtained from this system up here by multiplying through by epsilon. And when you multiply one differential equation by a constant to get the other differential equation, you're simply multiplying the vectors by a constant. The two vector fields are going to have exactly the same orbit because the vectors will point in the same direction, they'll just have different lengths. Our two systems have exactly the same orbits for epsilon greater than 0. However, the limits at epsilon equals 0 are entirely different for the two systems. For the slow system, if I set epsilon equal to 0, I'll get a 0 here and a 0 here. There's the slow limit system. The 0 on the left and one term is gone on the right. For the fast system, if I set epsilon equal to 0, this entire right-hand side goes away. This entire right-hand side goes away. This term here goes away. And what I'm left with is this very simple system for the fast limit system. The slow limit system and the fast limit system are entirely different. So is that a good thing or a bad thing? Point of view of geometric singular perturbation theory is that that's a good thing. What you can do, it turns out, is you can approximate the solutions for small epsilon bigger than 0 by so-called singular solutions. What are singular solutions? You combine solutions of the slow limit system and the fast limit system. These are much simpler systems, and we'll see. It's easy to figure out their solutions. And by combining them, you get a very good approximation to the solutions for epsilon bigger than 0, which in fact represent what's going on in the real world. Let's start by looking at the fast limit system. S prime equals 0, I prime equals 0, x prime is x, 1 minus x, k minus mi. Let's start like we would for any differential equation. Let's find the equilibria. These first two equations are always 0, so we just need the last equation to be 0. The last equation is 0 when x equals 0, when x equals 1, and when I equals k over m. Now, it turns out that this I equals k over m, those equilibria are not really important for us, but the equilibria at x equals 0 and x equals 1 are very important for us. Here is what this system looks like. This is the prism, s-axis, I-axis, x-axis. The points SI are in a triangle. X is between 0 and 1. If I were to set x equal to 0, I'm down in this triangle. Every point is an equilibrium. If I set x equal to 1, I'm up in this triangle. Every point is an equilibrium. Now, what's happening in between x equals 0 and x equals 1? Well, S prime and I prime are 0. They're not changing. So we're moving perfectly vertically. Only x is changing, not s and I. When I is smaller than k over m, here's the plane, I equals k over m. Remember, this was the I-axis. When I is smaller than k over m, x prime is positive, and the motion is straight up. When I is bigger than k over m, k minus mi is negative, x prime is negative, the motion is straight down. This is the orbits of the fast limit system. What about the slow limit system? It's not exactly even a differential equation because one of the equations doesn't have a derivative in it. It's just an algebraic equation. The way to make sense of this is to say that the differential equation given by the first two lines only makes sense when the last equation is satisfied. So we only use this differential equation when x is 0, when x is 1, or theoretically we could use it when I is k over m, but it wouldn't make any sense. If I fix I, it wouldn't make any sense to look at a differential equation for I dot. So this I equals k over m is not really of any interest to us. But we can fix x equal to 0 or x equal to 1 and look at this differential equation. Let's see what happens. Suppose we fix x equal to 1. That means we look at the top triangle. What do we have over here? We don't really have a weighted average of 2 betas anymore. When x is 1, this term goes away and we simply get beta n. Down here in the second equation, we simply get beta n. In other words, when x equals 1, what we get on the triangle is simply the SIR model with beta equal to beta n. We get the course of an epidemic when beta equals beta n. When beta equals beta n, R naught's bigger than 1. So as we saw before, epidemics can start and then they die off. There's an S value in here. This is the S-axis, where we switch from repelling to attracting equilibrium. What about when x is 0, down in the lower triangle? When x is 0, these terms with beta n go away. We just have beta c multiplied by 1. What we get is the SIR model for beta equals beta c. When beta equals beta c, R naught's less than 1, and that means the solutions all just feature I declining toward an equilibrium. Now, let's see how to combine solutions of the fast system and solutions of the slow system to get singular solutions, which are a combination of both. So suppose we start our epidemic off at some intermediate state. Most people are using normal behavior. Some are using careful behavior. Maybe they read in the newspaper that an epidemic has started over in China and they're already trying to be careful. But the number of infectives in the population is very low. Normal behavior is superior. And if we follow a solution of the fast equation, it just zips right up to x equal 1, where everybody's using normal behavior. Now we switch to a slow solution. This is a solution of the SIR model with R naught positive. Here in the picture I've drawn, the number of infectives increases. At some point, it crosses K over M. The number of infectives gets even greater than K over M. At this point, careful behavior has become preferable to normal behavior. And at some point, the population changes their mind and everybody switches to careful behavior following a solution of the fast system. So now we're down here at x equals 0, where everyone's using careful behavior. R naught's less than 1. The number of infectives decreases. When it passes K over M, people kind of want to relax. Normal behavior has become preferable. And at a certain point, the behavior changes very quickly as people switch toward normal behavior, following a solution of the fast system. So here we've got solutions of the fast and slow system put together to get what's called a singular solution. And the basic theorem of geometric singular perturbation theory says that if you look at a singular solution like this, starting with x between 0 and 1, then for small epsilon bigger than 0, a solution with the same starting point would be very close to this singular solution. Actually, it would never quite get to x equal 1 or x equals 0, but it would get close. It would follow along that solution and eventually it would jump, follow closely along the solution here and jump. The solutions for epsilon bigger than 0, which is reality, are close to the singular solutions as long as epsilon is small. Here I've simply drawn these pictures again. There are a couple issues with what I just told you. So let me focus on two of them. First of all, the pictured singular solution is not complete. We left it in the middle here of heading toward x equal 1. And second, I didn't tell you how to tell when a solution leaves x equals 1 or when it leaves x equals 0. What are the answers to these questions? The answers are that if you follow a singular solution far enough, it may jump back and forth a number of times, but eventually it will follow a solution that dies into an equilibrium at x equal 1. That's the answer to how you complete the singular solution. And the answer to when does the singular solution leave x equals 0 or x equal 1, that's given by a gizmo called the entry-exit integral. What is the entry-exit integral? As we follow along this singular solution in x equal 1, the plane x equal 1 is always attracting. The fast solutions are heading toward it. The way to think of it is attraction to the plane x equal 1 is building up as we follow this slow solution. When we pass I equals k over m, the plane x equals 1 becomes repelling. The fast solutions are leaving it. The way to think of this is repulsion from the plane x equals 1 starts building up. It builds up and builds up and builds up until at a certain point, the repulsion has built up to match the attraction that built up. And at that point, the solution leaves. That's very nice. How do we actually measure attraction and repulsion to x equal 1 or to x equals 0 for that matter? The same thing happens at x equals 0 so that we can predict when these solutions will leave. Attraction and repulsion can be measured by looking at the fast limit system. The fast limit system with these arrows heading straight to x equal 1 or straight away from x equal 1, straight to x equals 0 or straight away from x equals 0. This is the system to look at to measure attraction and repulsion. And actually, the quantity to look at is the partial of x prime with respect to x. This is just, well, k minus mi can be considered a constant. If you were to multiply this stuff out, you'd have 1 minus x squared. The derivative with respect to x is just 1 minus 2x. The partial of x prime with respect to x is 1 minus 2x times k minus mi. Suppose we look at this at x equals 0. Let's just get an idea of why this is a good way to measure attraction and repulsion. At x equals 0, the partial of x prime with respect to x is, these terms just give 1, you just get k minus mi. When I is greater than k over m, this partial of x prime with respect to x is negative. When I is less than k over m, this partial of x prime with respect to x is positive. Negative for big I, positive for little I. Let's go back to our picture. At x equals 0, the partial of x prime with respect to x is negative for I bigger than k over m and becomes positive for I less than k over m. You can see that the partial of x prime with respect to x is telling you whether there's attraction to x equals 0 or repulsion from x equals 0. What about at x equal 1? Then the partial of x prime with respect to x, if I said x equal to 1, it's minus k minus mi, and we get the opposite answers. For I less than k over m, it's negative this time. For I greater than k over m, it's positive this time, the opposite of what it was before. Let's go back to our picture. For I less than k over m, partial of x prime with respect to x was negative. At x equal 1, we're attracted to x equal 1. For I greater than k over m, partial of x prime with respect to x at x equal 1 became positive, we're repelled. Negative is attraction, positive is repulsion. How do you tell how attraction and repulsion accumulate and balance? This is by a certain integral, entry-exit integral, and we're going to look at it at x equals 0. It's totally similar at x equal 1. So here's a picture for x equals 0. We're going to start at a point S naught, I naught in x equals 0, where the partial of x prime with respect to x is negative. In x equals 0, that's large I. That's where solutions would be attracted here. Through that point, S naught, I naught, is a solution of the slow system in this plane. We're going to call that solution that starts at time 0 at S naught, I naught, we'll just call it S of t, I of t. You move in this direction as time increases. And we're going to follow that solution as time increases until a certain time t1. And that t1 is defined as the point where the integral from 0 to t1 of the partial of x prime with respect to x at the solution point S of t, I of t becomes 0. So partial of x prime with respect to x is defined at each point S of t, I of t on this solution down here. It's all going to be negative until the solution gets to I equals k over m. After that, it's all going to be positive. So you have an integral, it's negative for a while, builds up to be negative, then your integrand becomes positive. And if at a certain point the integral becomes 0, that's the point we want. That's where attraction and repulsion balance. So that will occur at a certain point, S1, I1, and that's where we leave. If this is where we enter, that is where we leave. And the basic theorem says that if you fixed a delta up here, x equal to delta, if a solution started at the point S naught I naught delta, that's right here, and for small epsilon greater than 0, we followed the solution until it got back up here at some point where x becomes delta again. This point where you arrive back here is very close to S1, I1, closer and closer as epsilon goes to 0. The entry-exit integral for x equal 1 is very similar with a small twist. For x equals 0, it turns out that as you follow this solution, that integral builds up to be an infinity as you approach an equilibrium. And what that means is that when x equals 0, you always will reach a time t1 where the integral becomes 0. There always is a leaving point when x equals 0. For x equals 1, that's not necessarily true. You see here, the integral builds up. Now it starts building up more and more positive, more and more positive. Whoops, if I cross back and the integral hasn't yet built up to be 0, it never will. Because once I cross back below I equals k over m, the integral starts becoming more and more negative. So in the case of x equal 1, it's not the case that there's always a leaving point. There may not be. There may not be a t1 where the integral is 0. In that case, what might happen is that the slow solution, you never leave, and it just continues to an equilibrium. In that case, for small epsilon, what would happen is that a nearby solution would follow this and die into an equilibrium, not necessarily exactly the same one, but a nearby one. It's a little hard to see this because I haven't drawn the pictures that carefully, but what can happen is the epidemic began, number of infectives were low, people used normal behavior, infectives increased. This is like a wave of an epidemic. Eventually, people freaked out, switched to careful behavior, number of infectives decreased. Eventually, people relaxed and headed back to normal behavior. And what can happen is that you again get a second wave of the epidemic. The number of infectives increases. You might leave again and get several more waves of an epidemic. This model is capable of producing various numbers of waves in epidemics, much like we see in reality. This was a very simple model, but it uses a good idea, imitation dynamics and changes in behavior. Are there ways we might try to make this model more realistic? There are lots of ways. I'll just mention a few that occur to me. One is you might want different compartments for different social groups because that fixed cost minus K of staying home is different for different social groups. If you're a professional who can work from home and still have your same income, the cost of staying home is not that great for you. It's easy for you to switch to staying home. Whereas if you're, say, a day laborer who needs to go out every day to earn some money to buy food, then the cost of staying home could be very great for you, and you might never do it. Another observation is that what we're calling the fixed cost of careful behavior might not really be fixed. For example, over time, people may just get sick of wearing a mask, staying home, never seeing their friends, never seeing their family. They may start to feel that that fixed cost of staying home is greater. Costs, game theory, are not necessarily monetary. They can be subjective. Alternatively, people who are staying home but don't have a source of income might exhaust their savings. And now to the previous cost of staying home gets added this cost of starvation. And now they need to go out and find some work. Changes in government requirements can also affect the cost of staying home. One of the costs of staying home for a lot of people is that they simply miss going out to restaurants, bars, and so on. If the restaurants and bars are all closed, that cost is not there for people. It makes it easier for them to stay home. When the restaurants and bars reopen, now they have that additional cost of staying home. They're not going to the restaurants and bars, which they could. Now the cost of staying home becomes greater, and they might want to stop staying home. Another idea for changing the model that has been used in some papers, the model assumes that people react to I, the present number of infectives. That's not necessarily the case. People might react to the memory of the epidemic, the memory of I of S for S less than or equal to T in some manner or other. For example, even when the number of infectives decreases, if people remember how terrible things were when the number of infectives was higher earlier during the epidemic, they might, because of that memory, be very reluctant to start going out. So we might want to change the model to have people reacting to memory rather than to the present state of I. Another observation is that people react to what they hear on the media. If they hear the epidemic is terrible, that'll make them want to stay home. If they hear it's really no big deal, just like the flu, they may want to go out. So we may want to have different compartments in our model for different, how should we call it, styles of media consumption. At present, the models that are used in practice do not take into account spontaneous human reaction to the epidemic, even though everyone knows it's important. There simply is not a lot of agreement on exactly how to model human behavior. There's not a lot of agreement on how to estimate the parameters, like the Ks that would go into any model. And so spontaneous human behavior change is ignored, even though epidemiologists are well aware that it's very important. This provides a challenge for those of you who have taken the course to see if you can contribute to more realistically taking into account human behavior in epidemiological models to the point where they can actually be used in practice. Thanks very much. This is the end of the lecture and the end of the course.